Okay. Hello, everybody. Hello, Balticon. We're a panel on the quantum internet, hype or reality, or since this is the quantum internet, perhaps entangled bit of both of these things. I'd like to first ask the panelists to introduce themselves. Perhaps Kevin first, and then Anne. I'll introduce myself, and then ask Kevin to put up some introductory slides on the quantum to get us started and to make some remarks, and then we'll get into the body of the panel. We'll start focusing on the panelists and then pull in stuff off the Q&A as seems indicated. But I want to give the panelists a running start, and then we'll pull in the assembled multitude as the panel progresses. So first, Kevin, would you care to introduce yourself?
Thank you, John. I'm Kevin Roach, and some of you may know me from my costume work, but I have been a researcher at IBM Research Almaden in San Jose for 37 years. Sorry, 39 years at this point. Uh, and my field is a branch of material science called spintronics. But along the way, I found myself giving talks to general audiences about the quantum mechanics of spintronics. And when IBM began its quantum computing program, I was certified as an IBM quantum ambassador to be allowed to talk to the public about what we're doing. So I will do my best when I'm talking to you to not be too confusing, uh, because that is actually my job as an ambassador.
Okay, Anne?
Hi, everyone. I'm Anne Gray. I've been around in science fiction conventions a lot. A lot of people only really know me as a con runner, but I did for a while. I was a physics major in college, and then I have a master's in systems design and engineering. From a young age, I thought I would end up in physics because already in junior high, when they were telling us that electrons went in an orbit, I was like, it's not like that. It's just a probability field that they're in there somewhere. And then they were told, you will learn that at a later time. And they sent me to the library, which was also fun. But I actually did take quantum mechanics in college, and even in electromagnetic theory, I was very interested in what aspects of quanta, subatomic particles, we could measure or observe, and where things were going with that. So I've been on and off keeping track of this as a subject, and I told a friend recently that unlike Kevin, I have pretty much a layman's interest in quantum computing, and she laughed at me, and I was like, oh, I guess most laymen don't really take an interest in quantum computing, but I do, and I'm looking forward to where this panel goes.
Okay, that's great. My name is John Ashmead. I am actually at the leading edge of research in a very closely related area. I have one particle on the relationship of time and quantum mechanics out in a peer-reviewed journal online. And I have a second article, a follow-up on how to do experimental tests of time and quantum mechanics in the nail-biting stages of peer review. I think I have placated my referees, and maybe I'm right. And they told me they're going to get back to me this weekend, so I'm under some little stress off that. But this is a kind of relaxing and enjoyable subject. I heard Kevin speak at Worldcon. He did a great job on quantum mechanics, so I was delighted to hear he could make it for this. He's going to open up our panel with a couple of background slides on quantum mechanics to help get us started on the subject. Then I've asked Anne to make some further initial remarks, and then I will start the panel proper with a few non sequiturs of my own. We'll go back and forth on a couple of subjects, and we'll gently entangle in the audience with their questions. So, Kevin, if you would take it away.
Certainly. So as I bring this up, these are a few slides from the talk that John saw. So there are gaps. Please forgive the choppiness of what I'm going to talk about. And But the important thing when we use quantum mechanics to build information technology is that we're taking advantage of the weird fuzziness that happens at the quantum level. So this is not the weird fuzziness of the Ant-Man quantum world. This is the real quantum world, which is even weirder. The first thing, which many of you may have heard of, is that there's a limit to how closely you can measure things. The most famous example is the Heisenberg uncertainty principle, which tells you that you can know how fast an object is, a particle is moving, or where it is, but there's a limit to the precision you can know both. And if you measure its position exactly, you no longer have any idea which direction it's moving or how fast. So this is just one of the weirdnesses that's there. Related to this is the idea of superposition. And Anne already mentioned that planets, or rather atoms, are not little solar systems. You don't actually have little electrons in orbits around a nucleus. What you have instead is a cloud of electrons as an energy wave. Now you can measure where it is at any particular point, and you can do that over and over and over. And if you do, you build up a map like is on the screen right now. And this is, I think, a d orbital. Might be a p orbital. I'm trying to remember which is the 2-lobe orbital. But this is actually a calculation from a supercomputer simulation. But it demonstrates the idea that we know where the electron can be, but we don't know exactly where it is at any in between those times. And we use this idea of superposition for lots of different properties. Position is just one. In computing, we use a couple of energy levels, and it turns out that things can be in mixed energy levels. That's superposition. If you need a real-world example, and you've ever played with a magic 8-ball, until you turn it over, there are 20 possible answers. So you could say those 20 answers are in superposition until you turn it over to read a single answer. Now, the next thing that we use a lot, and this actually affects not only quantum computing, but ideas for quantum communication and quantum encryption, is the idea of entanglement, which John very cleverly worked into the conversation twice already. You can, if you have two quantum systems, you can entangle one of their properties. It's now called correlated, and the two particles are said to be entangled. In this case, I have two little pink glowy balls that are a mix of up and down. And worse, they're entangled. Now, it turns out that the universe says when we get around to measuring, only one of them can be up and only one of them can be down. But until the moment we measure, they're both in equal superposition of both states. And more important, and what's really weird, is once they're entangled, you can physically separate them. And as long as you do it right, that entanglement persists. The longest distance done with this was entangled photons between the International Space Station and the ground. So it really does persist a long ways. And so what happens then is when you measure one of these, the state of both is determined because the total system requires that the scales balance. Now, you might think, oh, wow, cool. We can use this for faster than light communication because it's instantaneous. The problem is the people at the other end need to know when to measure, because if they measure too soon, they will break the entanglement. And the information about when to measure still travels at the speed of light. So we can't use it for faster than light communications, but we can use it to tie two ends of a communication channel together or to tie multiple systems together in a quantum processor. And that brings us to the qubit. Now, in a regular computer, we have bits, and I think most people have heard of bits in a computer, and many people understand they're essentially a switch. They're either on or off. They're a 1 or a 0. A qubit is actually an energy system. It's a very simple model of an atom that has two possible energies, and so it can be in superposition until it's measured. And this means it's actually really powerful, especially when we entangle them together. Now, the problem is you do have to measure it at some point, and then you're going to get either a 1 or a 0. To find out what the best answer is, you repeat it over and over, and you look at the statistics. So this is me running my quantum experiment over and over, and oh, look, 0 is the more likely answer. And that's how we use a quantum processor, is with multiple states. That's a single qubit, which is 1 or 0. It doesn't give you much over a regular bit, and it costs a lot. However, when you combine them and entangle them, they become very powerful very quickly. Each time you add a qubit, you double the number of states. In a regular computer, to double the number of states, you have to have twice as many transistors. So the equation is 2 to the n. We call these basis states. And to give you a real example of just how much power we're talking about, the way we talk about it now is when you're building quantum circuits, that's the jargon for an actual program using qubits, you can simulate how that works by using a regular computer up to a point. So as you can see here, to simulate 2 qubits, which is four of those basis states, it takes 512 bits to properly model them. And it goes up and up very, very quickly. When we get to 35 qubits, properly entangled, it takes 550 gigabytes. So 8 times 550 bits to be able to simulate what they do. And you get to 160 qubits, which you can't. And we actually now have real quantum processors that are larger than 35 qubits. So the power of the qubit and the quantum processor scales very quickly. That's why so many people are excited. And with that, I will stop the share because that's the last slide. And I hope that wasn't too confusing.
Thanks very much. And would you care to pick up with a few remarks of your own?
One of the most common questions I get as ambassador is, are quantum computers, how long till a quantum computer breaks encryption? And this over and over and over. That's one of the first 2 questions we always get asked. And the answer is yes, a quantum processor with enough qubits can factor large numbers very, very quickly, which will break RSA encryption, the most common kind still in use. However, breaking encryption is an ongoing battle always. Every time we find a better way to encrypt, someone finds a way to break it. And so there is now industry effort to develop quantum proof encryption techniques. IBM has a whole department that is specializing in developing some of these. We're not the only people. One of the most promising is something called lattice encryption, and it's already used in some of our data tape drives. And it cannot be broken by large number factoring. So so we can put that particular question to rest right away. Yes, a quantum processor will be able to break RSA encryption at some point, but by the time it can do it, everyone should be using a non-factoring kind of encryption, so they're safe from it.
That's okay. That's very good to hear, actually. Yeah, I have a follow-on comment to the FTL remark, but I first want to hear from Anne and her opening comments.
Sure, thank you. So part of what led to this particular panel as a prompt was there have been a whole slew of articles on Schrodinger's Web or Schrodinger's Internet. There's actually a book called Schrodinger's Web, Race to Build the Quantum Internet by Jonathan P. Dowling that came out recently. And Dowling has also written an article, I forget which magazine it came out in. Quantum computing has been used for encryption purposes for a while now. And according to Dowling's book, there was a period in which, at least in the U.S., we kind of figured we were at the cutting edge of quantum computing and its various applications. And then we sort of had a Sputnik moment with the Chinese and realized we were actually like 10 years behind them or something. So now there's a whole Chinese area of research, and we actually created a U.S. National Quantum Initiative in 2018 to try to catch up, to say, well, okay, so one of the interesting things about these entangled quantum particles is that they don't have to be close to each other, right? You can have them in a circuit right next. I mean, you can have the circuit be dealing with these potentialities, but you can also have these entangled particle pairings. You can spread out where that information is going to be. You can basically, Einstein once called it, spooky action at a distance. You can kind of like have this almost psychic seeming link with another location, as long as they have one of the paired particles and you have one of the paired particles. So how does this work? Well, obviously some of our quantum particles or qubits can be represented with electrons or photons. And so we can, to a certain extent, most of what I've seen as far as creating a quantum internet covers moving those things around with lasers. So you guys can talk more about that. It's still, generally speaking, an expensive and potentially dicey proposition, because you need to watch out for decoherence of your signal, of the entanglement. And so a lot of the early development in quantum computing and stuff, a lot of your equipment was kept very cold, these sorts of things. And so there was sort of this perception that only really rich corporations who could use really fancy technology would be able to do that. And Kevin can tell us more about how IBM's trying to convince everybody that that's not true. And it's a more approachable technology than you were originally told. And but it's that question of how far apart could we potentially put these things that can calculate and can, in a way, communicate with each other. Just because if you collapse the state of one of that pair, you know what the state is of the other one, no matter how far away it is. And it could be out in space, right? We could have communication between telescopes that are really far away, doing calculations on what they see, even though they're apart from each other. There are all kinds of exciting possibilities, but so that's kind of that question of where are we going, and is this really going to be practical? Is it going to be something that only really rich people can use, or really high-tech countries? Is it going to be controlled by the Chinese and the Americans, or are we going to put it out there in the world so everybody can use it?
No, that's great, Anne. And I read through Dowling's work. Unfortunately, Dowling himself died recently, and somewhat unexpectedly. He was a great evangelist for the quantum internet. And one of my skeptical questions on this is precisely the point that you're bringing up, that it is very hard to move quantum information across large distances once you have to repeat it. And one of the things that makes it hard is something called the no cloning theorem, that if you move quantum information you can't get quantum information from one place to another by making 10 copies of it and hoping that one gets through. You're not allowed to copy a quantum system. You can only move the information as a whole to the next stage in the process. And the theorem that says this, the no cloning theorem, you can't make a copy, has a very interesting starting point. In 1982, a celebrated popularist of science, Nick Herbert, wrote a paper on how to send information faster than light. He invented a communication system for this called Flash, which he sent to a physical review, I think, to be published, which would send information faster than light. And the reviewer said something absolutely brilliant. I know this paper is wrong, but I don't know how to prove that. Let's publish it and have the community find out why it's wrong and see if that doesn't tell us something. And within a few months, Wouters and Zurich invented the no cloning theorem because they said Herbert assumed you could copy a quantum system, and you can't actually do that. So his error was far more productive of understanding than a predictable truth might have been. And I'm hoping that something similar will come out of the quantum internet. I'm a little skeptical of all the plans I've seen so far, but I think all these really smart people pushing hard to make it happen will find things that are of even more value than what we're anticipating now. That I think we're going to get some valuable errors out of this, and our effort to make this happen will be extremely productive, even though the specific approaches have really very don't look all that practical, at least with current tech. So the components of the quantum internet are, of course, quantum computing itself, some kind of long-range entanglement, which we've seen from satellites down to Earth, like the thing you mentioned about the International Space Station, quantum repeating by linked steps of entanglement, which has been demonstrated in principle really more than in practice, quantum sensors, and the birds appear to be using this for detecting magnetic fields. So if the birds can do it, we have to be able to do it too, sooner or later. We'll take a flyer on what the birds are doing. Quantum punning, by the way, is an underexplored area. You go from quantum entanglement to quantum punning in a single step. And if you can't quantum pun, you just can't pun at all. I apologize for that, or I should apologize for that. So we have a lot of components to the quantum internet. And the metaphor of the quantum internet, because we understand the regular internet, will take us to say, well, this is an interesting question, this is an interesting question, this is an interesting question, and we'll link together a whole bunch of interesting questions like the quantum cloud and quantum intelligence, and these will take us to the next level. So I expect a lot of productive errors. And if we survive all the errors we are certain to make, we may accomplish something quite wonderful. Any response from my co-panelists on that?
Would you like me to address the technology questions a little bit deeper?
That would be great since you're well positioned, and that'll give Anne a chance to recover from all the quantum punning.
Well, the very fact, the very fact that they named them qubits, that's the base pun of quantum computing, because we use them to do everything. So Anne mentioned the use of lasers. In a quantum processor, as I mentioned, we're essentially building a model of an atom that has two energy states. There are many different ways to do that. The most common right now are what's called a trapped ion. So that's an atom with one electron removed. So it's got a charge. Because it's charged, you can hold it onto a chip very easily. And then you can excite it into one of two energy states by hitting it with a properly tuned laser. To scale this up requires that you do micro or nano level optics to bounce the laser beams around. So, and they're really stable. They have individual qubits have nice long lifetimes. You can actually build them into a chip, and they don't have to be cold. But they're also, because of that, harder to manipulate because they are so stable. But there is lots of research being done with trapped ion qubits. The other big one, which is the one IBM is using, and Google, is the superconducting transmon qubit, which is essentially a little microwave oscillator that is anharmonic. So it has more than one resonant frequency, but they're not multiples of each other. So if you ping it with one microwave frequency, it will ring, it will resonate. If you ping it with another one that's not a multiple, it will resonate at that one. And you can tell the difference because the two frequencies are not multiples of each other. So I describe this as, we sing to the qubit with microwaves, and then it hums back to us when we measure it. And then there are various things you can do to...
When the wavelengths are multiples of each other, then if you can basically feed a harmonic with something else that is not the exact same, but is just a multiple of it, because the waves
Well, you can't tell which one it is, right? So
Right. You
if your
can't
two
tell which one it is.
yeah,
Yeah.
if your two energies are 2 and 4, you can't tell if and you're in state 4, you can't tell, or rather in your state 2, it gets very hard when you're measuring frequencies. So having them be 3 and 7, those you can tell apart because neither is a factor of the other. So that's what they look like. In fact, you mentioned again resonance. That's how we actually entangle them. Turns out that if you have a little antenna connecting two of these superconducting transmon qubits, and you ping qubit 1 at qubit 2's frequency, a little energy will go along that antenna, and that entangles the two of them together. Because you've excited number 2 via number 1, and that actually entangles the states of the two. When I found out it was that simple, my jaw dropped. Because they kept talking about entangling the qubits, and nobody ever talked about how they did it. And I cornered one of the scientists and said, how do you actually do it? So
but that's part of why you can't copy them, right? Because it actually is a relationship between two actual things.
Yeah. So if you look at one of the superconducting transmon qubit chips, you can see the circuit. The qubit space itself is visible to the naked eye. The thing that makes it anharmonic is not quite visible to the naked eye. You can see it with optical magnification. So you can get a bunch of these in a chip, and you don't need fancy technology to make them. You can just etch them with a regular circuit board system. And now getting everything tuned so that you don't get crosstalk, you don't get noise, those are the technical challenges of building bigger chips. And in fact, I don't know all the secrets of our current big chips. We've now passed the 100 qubit point in a working processor in one of our systems. The ones I have pictures of are all the 4 and 8 qubit ones. And you also brought up the question of access. The reason I was willing to become an ambassador was in 2016, IBM made our quantum processors accessible to the public on the web for free. And they still are, and the ones that are available for free keep increasing in power. So if you search for IBM quantum computing, you can go to a website, create an account, and you can log in and program a quantum computer. You can't do a lot with them yet, but it's all open source software, so we're using the power of everybody who wants to program a quantum computer to make them all better.
Could I? Yeah, there's a question in the chat about how you program a quantum computer. Is there like a special Q language for this?
So each company has their own. The one that IBM has developed is called Qiskit, Qiskit. It's Quantum Information Science Kit. Yeah, Quantum Information Science Kit, Qiskit. You can go to qiskit.org. It's this giant open source community. And we just released a new library, and I have actually managed to install the language and the libraries onto a Raspberry Pi. So I have a Raspberry Pi that can send jobs to the IBM quantum computer and get the answer back. So these are hybrid systems. You write your code locally, you send it via the web to our teams. It goes in a queue, and when your results are done, they show up in your account, and it emails them back to you. And then there are more advanced processors that universities and business partners can join the IBM quantum network, and they get access to those. But the public ones are always in use. We have millions of users at this point. So
can people sign up to get email from your Raspberry Pi? Is that?
My Raspberry Pi, actually, they just released a new version of the libraries, and I haven't had a chance to update it, so I don't know if the code runs right now. That is the problem with an evolving library. Is the Raspberry Pi is a hobby project that work likes, but keeping my lab running is more important most of the time than getting to play with my Raspberry Pi.
I would like to interject a note to my fellow salivating programmers out there. I have myself a Raspberry Pi, which costs $35, and Mathematica, which I paid $1,000 for on my iMac, can be downloaded on my Raspberry Pi for free. So what you're telling me is I can put Mathematica on a $35 Raspberry Pi and set up calculations to run on a free quantum computing host hosted by IBM. Well, I'm staying on this panel until the end of it because I said I was going to do that.
Um,
Yeah.
so,
Okay.
Your
Uh,
hands moving. We'll
and
know
and
what it
I
is.
I see. Yeah, you mentioned we have some questions in
yeah.
about programming. So the actual programming on the IBM chips is done via shaped microwave pulses, and so there is a what we call a transpiler that takes your source code and figures out what those operations actually mean, what gate operations. Those are shaped pulses that we use to rotate the energy levels in the qubits, entangle them, disentangle them, and then measure at the end. So you write the code saying what you want to do. It turns out into the shaped pulses, and it optimizes them so that it can do it with the least number of pulses. Every pulse you send down into the refrigerator is energy, which means it's increasing noise at the quantum level overall of the system. Chaos is our enemy when it comes to quantum computing. And then the measurements come back, and then it formats that and sends the data back to you. So you can do this iteratively. So people are doing that for materials science and quantum chemistry, and they're already testing machine learning and AI algorithms using this. These things that need large amounts of data where you need to correlate what's going on, that's one of the most exciting possibilities for the use of these quantum processors. And, I'm still agog that we're doing this and that we let everybody play with it. And the day I found out it, I pulled out my iPad and logged in, and I was able to write a program on my iPad and run it on a quantum computer. Uh,
Okay. And do you want to comment on this or continue?
I sorry, I was thinking more in terms of what John, you had said about, if the birds can do quantum stuff to detect magnetic fields, so can we. In point of fact, I mean, of course, quanta are just that subatomic level of reality, and we've been doing quantum science all along. I did a research paper on the history of electromagnetic recording and was interested to find, when I went around, talked to a bunch of professors about it, they were all like, well, we think it's maybe a spin effect. This was in the 90s. But spin is one characteristic that we can use to describe quantum particles, and it's sort of like angular momentum in a way. Anyway, it's like an energy level that they have, and it's that thing. Well, what is magnetism? Why do some atoms all line up in a particular structure and others don't? Well, it's because everything in the universe has already had quantum aspects, and worked that way. We just weren't aware of it until the last century. So we're still catching up, and who knows still if our next level of understanding will tell us that our technology that we're developing in this decade is actually based on even more science that we don't truly understand.
It sounds from your comments that you read the introduction to my current paper.
Oh, don't think I have.
Because I have to discuss measurements of time of arrival when I'm looking at time in quantum mechanics. And I go through all of the existing theories about this and show that each is defective because it has secretly snuck in classical assumptions which are not justified. And I actually talked with one or two of the authors of these things, and they got, like Avi Marchuka said to me, yeah, you've got a point there, and I want to see what you're going to do in response to that. And I think that what is holding us up on a deeper understanding of the quantum is an insistence on fitting it into our classical concepts. And that one of the things that I'm hoping for from the quantum internet and quantum computing is it will gradually force us away from our implicit reliance on classical ideas into a deeper, more full-bodied quantum mechanical approach to things. And we have to take the position, if you remember Carroll's Through the Looking Glass, where Alice walks through the mirror and then sees our world from the far side of the mirror. It's not until we see our current existence as strange and quantum mechanics as normal that we will understand either.
Yeah, that reminds me of kind of early on in this science, there was a conference at which Richard Feynman, who's one of my favorite physicists, and another scientist whose name I unfortunately don't remember, were both working in the area of quantum probabilities. And Feynman had invented a diagram basically representing how, you know, one particle could have different probabilities in different states, lots of different states, and then they could collapse into a single state. Or, you know, the relationship between states, between particles, I don't think he had quite gotten to, but we're still looking at matter and antimatter and all these things about probability, and people were talking about, is this happening in a different dimension? Why can't we see them all the time? You know, what happens? What's the difference between what we can see, what's possible, all this sort of stuff. And so him providing it a diagram, a lot of people were like, no, I don't think you can draw this. You know, that diagram's too simple. It can't possibly be representing the complexity. And the other scientists at the same conference had come up with some very elegant equations to talk about the same thing. And so the whole weekend, the conference was in a big uproar. People were taking sides. It's this, it's that, he's wrong, he's right. And eventually they concluded that both the equations and the diagrams were saying the same thing.
Yeah, Feynman was very fond of saying that if you can't explain the basics of the idea to a freshman, you don't entirely understand them yourself. He was a great teacher, and a number of his videos of his original lectures are now available on YouTube. And it's like a master class on how to teach people anything. I'd like to take a quick look at a couple of the questions in the Q&A, since we are actually having so much fun that the end of this talk is already sneaking up on us, which is amazing to me. And one of the ones, here's a good one from Bill Horst Cotter. How would a quantum computer interact with other parts like RAM and hard drives, or would they have to be written on quantum memory and storage? Can we isolate the purely quantum part and let it talk to other classical systems that we understand? Or do we have to make the whole shebang quantum before we can really get going on this?
So that is actually what we're doing right now. We do not have quantum memory or storage. The entire processor is reinitialized at the beginning of each run. So there are people working on ideas for at least you might think of a register, you know, a temporary storage register in a processor, but there is not RAM or disks or storage like we think of in a classic computer, which is part of this hybrid model. I mean, one of the other questions we always got early on in the IBM Quantum talks was, you know, well, is this what about a hybrid computer, you know, using classical and quantum? And in fact, that's what they all are. You know, the quantum processor does the thing that it's really good at, which is manipulating these very large, very complicated models with many possible states. And the rest of it, setting it up and then feeding it in and then reading it out, has to be done with classical technology. So it's always going to be a hybrid system. There are people looking at theoretical ways to add memory to quantum processing, but that is not in my experience, so I can't address that. I do know work is going on, and there are many arguments about it also, whether it can be done. The real key is right now there are ways you can essentially put diagnostic qubits into a processor so you can get signs of what's going on, but to actually take a snapshot inside the processor, that's a measurement which can then collapse the entanglements. So you need to let it do its work before you measure it. And that's one of the challenges. That's one of the big differences between how a classic processor works and a quantum processor. There were a couple other, Ben B asked if the 100 qubit chip could store more information than all the traditional hard drives. It doesn't store information, but it can process this giant number of combinations. And there are other quantum mechanical tricks they use with interference. So the best answers come out interfere constructively, and the bad answers interfere destructively. So when you measure, you can actually get the peak in the data with a smaller number of shots, a smaller number of experiments by designing it right. And they have not managed to explain how they use interference successfully to me in language that I understand, but it is a key component of quantum computing. Entanglement, superposition, and interference are the three keys that make the processors powerful. And I still don't quite get the interference part. I know what it does, but not how.
Yeah, the quantum memory is going to be key as well, because it's not only needed to get a full-scale quantum computer working properly, something that can be less transient, but apparently it's needed to get quantum repeaters to work correctly so they can accumulate some of the entanglement and not have everything have to work perfectly at a single instant. And I think this is my picture of the quantum internet, is that there are a couple of key points in it, all of which we have to ultimately make work at some level, and all of which are interesting. And we're just kind of pushing forward in all sorts of directions, hoping that we will have breakthroughs here and there. Your comment about it being difficult to monitor the quantum CPU makes total sense because of quantum theory and the measurement rules. But I know one of our problems with regular classical AI is that it's very difficult to figure out how the AI came to its conclusion. And until we can understand how the AI arrived at its conclusion, we are not going to trust it to run nuclear reactors or to do medical things. It's got to explain itself before
Where we are now in processors is we have essentially naked qubits. And part of the model for how this will evolve is we will be building layers of qubits. So then you have a logical qubit, which is actually many physical qubits. And so the physics does the error correction for us. It does the fault tolerance and the error correction so that all this tweaking that we do by hand, the processor is actually doing it itself because of its design. Just like we have error correcting memory now, the idea is that we will be building into the actual structure of the processor with extra qubits and extra quantum mechanics to reinforce the way we want things to run and to clearly tell us when things aren't working. So, our processors now are moderately primitive, but they're already doing remarkable things.
So Kevin, IBM are obviously working on processors. Do they also have a project on the quantum internet extension? And can you tell us anything about it?
I can't. That's actually not part of my brief. I'm sure there is somebody. I know we work on encryption, quantum encryption papers. Ike Chang was an IBMer, the man who. Right. So the original trapped ion work that led to his papers on quantum encryption that came from IBM. So we have a long history with this technology. What I am taught about to tell the public is more aimed at our expansion of quantum computing itself, but also awareness of the encryption requirements. So much is moving into the cloud. That's actually a major part of IBM's work right now. I'm actually in the middle of taking a course on learning to do cloud development. And that actually, you commented on needing big refrigerators. That's one of the keys, is you can have a quantum data center where you've got all the refrigerators running as efficiently as possible and as resource spare as possible. And then we use the regular internet so that everybody has access to it. So it's like the old, it's a data center model. It's like sending your card deck to the reader at the old computer lab.
I was thinking of that, especially the old computers that didn't really have permanent memory.
Yeah.
You'd
I
have to
remember my 1-5 jobs at Princeton. We've gotten the 5-minute warning already. So, which is, wow. I'd like to ask the assembled multitude of panelists to each pull a question out of the increasing stack of questions and deal with it. And then we'll have a quick last licks on this thing. If you want to, do you have a question you'd like to pick, Kevin or Ann, and just deal with it?
There are a couple of related ones that actually. James Thomas asked if storage is not equivalent to copying or cloning. And early on, there's a question about what about we can copy a photon in a laser. How come that's not cloning? When we talk about cloning in a quantum state, we are talking about duplicating all of the quantum state information of the quantum system. So all of the qubits, all of their quantum information at a moment in time, instantaneously being copied into a complete and faithful copy of it. That's cloning. In a laser, you are actually doing stimulated emission, so you're getting multiple phonons with the same energy, but they're not the same phonon, and they're not the same photon, rather. So that's that's the difference. They all do have the same energy. They're from the same atomic transitions, but they're not clones of each other. They just are from the same energy states. And storage is where you move things when you're done calculating. So the difference between storage and memory, storage is where you write the file and it sits there. Memory and the processor are where you act on the data actively. So I'm having to relearn all this stuff right now in my cloud development course. So those answers are fresh in my mind.
Excellent. Ann?
I really like Richard Alt's question about how long we can keep the disentangled. Well, I'm not really sure if he means this. The disentangled pair in the initial disentangled state.
I think he means entangled.
I think he means entangled pair in the entangled state, and are there any theoretical bounds on this persistent state? And Kevin, do you know the answer to that? Do we?
The theory is there are no limits, but that's in a perfect quiet universe.
Right. And instead we actually have a tendency to lose energy, and things descend into chaos even if we don't mess with them. So yeah. I mean, that's the problem. Like even if we don't mess with something, possibly something else in the universe would.
The background microwave energy of the universe.
Right.
The energy of space-time.
Random neutron.
We are, by the way, getting the 2-minute warning, and so very quick last licks on this. Very quick. Kathy, our tech host, is being nice, but I don't want to stress it because I have to see her next year too.
Well, somebody else asked, when is the fourth Steve Jobs going to build this in his garage? And of course we don't know, but IBM is clearly right there to try to make it possible. And we all want to see this leap forward. As somebody was mentioning in another panel I was on, science and technology don't proceed in a linear fashion necessarily. We often have leaps. Marie Vibert was saying this, and that's part of the exciting part. I think if we get enough minds crunching on this and enough qubits crunching in the background, who knows where we could go with it.
And I am more than happy to respond to questions from people who want to contact me at my IBM address. And I may be able to find a local Qiskit advocate who can talk to them in person or present to their club or any. That's what we do. Obviously, I'm gung-ho about IBM because I work for IBM. I do not want to dismiss the hard work being done by other researchers, but I really like the way we're doing it. And I can say that honestly.
Okay, and I, for my last licks, will say that I think the most critical frontier in this is actually having a good mathematical description of quantum information. That my own sense is that our information metrics now are too firmly rooted in classical understanding of information. That was a slightly abstract comment, but we can follow up on Discord now that we have clearly hit time.
And we do have more quantum. We have a lot more quantum characteristics that we could be using if we had good mathematical models to use them.
Yeah, like we don't have a good mathematical model of how much information is stored in a spin state.
Right.
our model is of how much information is left after we measure the spin state. So I feel we're not seeing information from inside the quantum, we're seeing information from outside the quantum, and that gets back to my comment about Alice and going through the mirror. Okay, we will be on Discord for a while. I want to thank the audience and for their questions, and the panelists for their time and enthusiasm. So take care, everyone. And Kathy, I think we can bring this to a close now. Thank you.
Thanks, guys.